Hello everyone, and welcome back to another math video by me, Jake the Tutor. And this time, in this video, we're going to kind of wrap up a bit of the graph transformations series I've been doing with the scaling portion of it, which is essentially a stretch or a shrink in a graph, which like in my opinion, yes, it does kind of transform the graph, but in all honesty, if you're going to do the scaling, it's probably going to be in the function already. But it's important to know how these, like how the scaling works, just so you kind of have an idea of what to expect. So, scaling is best seen in a parabola. Like in the previous videos, we've been just using straight lines of like the slope 2, but scaling is a bit more obvious when we use parabolas or parabolic type shapes and graphs. So I'm going to use probably arguably the most basic parabolic function, which is f of x equals x squared. Alright, so let's go ahead and just, I guess, just plot some points on x squared. So when x equals something, we're going to see what x squared will equal, or in this case, f of x. So, I mean, we all know how to multiply a number by itself. So when x is 1, x squared will be 1. When x is 2, x squared will be 4. When x is 3, x squared will be 9, and so on and so forth. So let's go ahead and plot these points on our xy coordinate plane here. So when x is 1, right about here, x squared, or y, or f of x, will be 1. When x is 2, so there's 1, there's 2, x squared will be 4, which is located right about there. When x is 3, then x squared will be 9, which is going to be right up here. And that's all the room we have on this one, so that's where we're going to stop. So then you would just kind of connect these in a kind of curved fashion, even though I'm probably going to not do very good, but that's not terrible. So yeah, that's going to be one half of it. And of course, since when you square something, even when it's negative, it becomes positive again, because two negatives, when multiplied to each other, will equal a positive value. So we can do this same thing in the negative direction. When x is negative 1, y will be 1. When x is negative 2, y is still just going to be positive 4. And then when x is negative 3, y is going to be 9, still positive, and then we connect to the points kind of in a curved fashion, and there we go. So there is the best parabola you ever saw. Okay, actually not, because it's really jaggedy. So that's x squared, the best I can do with computer drawing tools that are available to me at this point in time. So since we're talking about scaling here, like we could shift this graph around, up and down, left and right, flip it across the x-axis, flip it across the y-axis, but we've already done those with straight lines, and doing it with the parabola would be a bit redundant, so we're going to focus on the scaling aspect of this. And scaling is essentially accomplished by multiplying a graph by some number. So in our case, let's just keep it simple. Like right now, it's f of x equals x squared, which could kind of be said like equals 1 times x squared. Let's instead multiply it. Let's call it a different function and use a different color, such as this red. We'll use red, and we'll say that g of x will equal 2 times x squared. So we've scaled it by 2. So what we're going to ask ourselves about scaling is, what will this do to our original function, f of x equals x squared? Is it going to stretch it? Is it going to shrink it? Is it like, yeah, so what's it going to do? Well, we'll have to go back to our t-chart. or yeah, our x versus 2x squared chart, kind of like we did above, but this time with our new function. So something like this. So when x is 1, x squared is 1, but then you multiply by 2, so this becomes 2. Alright, when x is 2, 2x squared, so will equal, alright, so x squared is 4 times another 2. 2 times 4 is 8. When x is 3, 2x squared, x squared being 9 times, and then you multiply that by 2. 2 times 9 is 18. Alright, so let's plot these points as best we can. Actually, we might not even be able to because we don't have nearly enough room, but we'll try our best. Alright, so when x is 1, y will equal 2. So there's that. When x is 2, y equals 8, which is going to be right about here. And when x is 3, y is equal to 18, which is going to be way up, probably even up here-ish, so we won't even be able to reach it. And we'll see that if we take the negative of these x values, we'll get the same thing in the y direction. So we'll just go ahead and plot these points about like that. So this is going to end up, it's going to look something like, oh man, look at that. Yes, perfect curve. I love it. Alright, now let's connect the other side. Oh yeah, look at this. Oh yeah. So we connected them as best we can, and even with my very jaggedy lines, we can see that this graph actually became thinner than the original one, but we multiplied it by 2. So this scaling shrank it, or I don't really know what the technical term is for this one. I call it shrink it, as opposed to expanding it. So let's try to take the opposite of this. Let's go with blue, and instead of multiplying by 2, we'll multiply by a half, and we'll see where that gets us. So we'll call this h of x, and so we'll do 1 over 2 times x squared, and let's go ahead and quickly make comparison chart, or a t-chart as some of us call it. So when x is 1, alright, what will this equal? Well, 1 squared is 1 divided by 2, so this is just going to be a half. I'm just going to call it 0.5. When x is 2, this is going to be 4, so so 2 squared is 4, divided by 2 is 2. Yeah, and when x is 3, x squared is 9, divided by 2, that's going to be about 4.5. And we could continue plotting these, but the 3 points should be enough to get the point across. So let's go ahead and plot these. Where are we at? Okay. So when x is 1, y is a half. So that's going to be right about here. If we can see that. When x is 2, y is 2. It's going to be right about there. When x is 3, y is 4.5. So here's 4.5. And already you can tell kind of what the pattern is here. These points are clearly on the outside of our original line of x squared, or curve rather. It's not really a line anymore, but yeah, the point is when we connect these dots, these clearly make a parabola that looks something like that. I mean, I haven't plotted what x equals at 4, so it's a little difficult to kind of predict that, but you get the point. These points all lie outside of the original graph of x squared. So, alright, so the trick to scaling is going to be a little hard to do this, but so just kind of as a summary, so we plot regular x squared, we get the black curve. This is the parabola x squared. When we multiply by something greater than 1, actually no, yes, greater than 1, or 2 in this case, we shrink it something to something less, or to something that looks thinner than the original one. And when we do something less than 1, like half, we actually get things that are wider than the original. So I'm gonna see if I can actually no, I think that'll suffice. We can see this easily on, let's say, a graphing utility. I like Mathway has this pretty cool thing on it that you can type in equations and stuff. So I'm going to go y equals x squared, just to kind of show you that I'm not just full of it. Y equals 2x squared. I'm going to plot these same graphs, and you will see that what I'm saying is true. There we go. So once they calculate that, we see that these curves are much more smoother, are much smoother than what I could even hope to do. But we see that the first graph is red, which is in between the two of them. When we plot the blue curve, or the ×2 scaling, it becomes thinner than the original one. And when we multiply by a half, which is less than 1, we get something wider, or something that stretched it longer than the original graph. So that's basically all scaling is when you multiply by something greater than 1, it becomes thinner, and when you multiply by something less than 1, it becomes wider. So that's all I have to talk about scaling, and that essentially wraps up graph transformations. So in the next video, I'll probably work out some problems you might expect to see in a homework regarding graph transformations. So until then, make sure to review all these videos, because in the next video I will be putting out some practice problems for you to look over, and I'll work them out step by step. So I'll see you in that video.